It's a sign of the times that at the start of this project we avoided the use of the Raspberry Pi in graphics mode entirely. The first Pi design that appeared in February 2012 was interesting, but just too slow and unresponsive to be useful. With the improvements introduced with version 2 in February 2015, with more memory and a more powerful processor, the Pi is now far more responsive. Current developments mean that even more improvements are on their way. In this project, we're going to be cruel to the Pi, making it work hard, really hard, and during this course we will see it struggle to perform your commands. With that said, welcome to this video on OpenSCAD 3D modelling. As with everything else in these courses, the software we're going to download, install and use is entirely free, all thanks to the wonderful efforts of the people who contribute globally to open source software. The package we're going to use is called OpenSCAD, where SCAD stands for Solid Computer Aided Design. It allows us to produce images that are not just flat two-dimensional affairs, but full 3D, three-dimensional objects that later we could animate or fabricate on a 3D printer. Grabbing a copy of OpenSCAD for the Pi is simple, as it follows the well-trodden path that we've used to install all of the other packages in this course. If you're at school, you will first need to run our special command that gets us around the protection of the county's firewall. We all know what that is. And then follow that by entering the command apt-get space install space OpenSCAD. Patiently follow the on-screen instructions, and when the prompt returns, jump to the graphical mode by entering Start X. Click Menu and Graphics, and click on the New option of OpenSCAD to start the program. If all is well, OpenSCAD opens with its user interface, displaying three panes: the text editor, the console window, and the viewing area. And it works like this. Click into the text editor pane and enter sphere, brackets 30, close brackets, semicolon. Notice that the semicolon has appeared again. We like to think of the semicolon as being short for please, as it completes a command. Nothing appears to happen until you press the F5 key. Now the sphere appears in the display window. Left mouse click in the display window to manipulate the sphere. You can drag it to move in all three dimensions. Right-clicking and dragging shifts the window in a flat two-dimensional view. Zooming in and out is possible directly if you have a mouse wheel. Otherwise, hold down the Control key and press the plus and minus buttons on the keyboard to achieve the same effect. In common with other windowing systems, the size of each pane can be set by clicking on the edges when the cursor changes and dragging them to suit your requirements. The console window lists the actions taken by OpenSCAD. You may want to reduce its size to give more space to the display area, but do watch the contents of this window. Stop the video now and become comfortable moving the shapes around the interface. This section introduced OpenSCAD user interface with a text editor, console window and display areas, and the basic keyboard commands used to control the display. In the editor window, enter cylinder 40, sphere 30 and cube 35 and press the F5 key. This strange shape displays all three of what is known as primitives. The three primitives are sphere, cylinder and cube. Click in the view window and manipulate the scene to see that all three primitives are stuck together. Notice that these axes move with the shape. The small color key shows red x-axis, green y-axis and blue z-axis. We've already seen the sphere primitive, which is centered at the origin of the three axes, where they all come together. This is the cylinder primitive. If the sphere turns transparent, we can see the cylinder starts at the origin, as does the corner of the cube. This is the default starting location for all primitives. I turn the sphere transparent by placing a percentage sign in front of the word sphere. Stop the video now and try by replacing this with other modifying characters, a star, a percent sign, hash, or an exclamation mark, to see what effect this has on each primitive. Don't forget to press F5 each time to see the effect take place. In this section we saw the three basic shapes used in OpenSCAD called primitives: sphere, cylinder and cube. We also saw how these primitives combine and are referenced to the origin of the X, Y and Z axes. We also saw the effect of prefixing the primitives with modifier characters, a star, hash, %sign, and exclamation mark. Returning to the editor window, we can delete the cylinder for a moment and move the cursor to the top of the window and add difference, followed by a pair of empty parentheses and open curly brackets, and place an empty curly bracket at the end. Press F5 to reveal the difference between the sphere and the cube. Notice that if we return to the editor window and relay out the command to make it a little more readable, nothing changes when we press F5. This is because spaces and blank lines, known as white space, does not matter in OpenSCAD. So, lay out commands to be easily read. In fact, we can add comments behind a double slash, which is not meant for SCAD to draw, but are helpful to humans. Replacing difference with intersection and pressing F5 produces this shape, which is the overlap between the sphere and the cube. To complete the set of 3 Boolean operators, replace intersection with union, and pressing F5 returns us back to the initial state of the sphere and the cube stuck together as a union. Stop the video now to discover how many different shapes can be made. Is the cube subtracted from the sphere the same as the sphere subtracted from the cube? In this section, we looked at the Boolean operators, the union, difference, and intersection of primitives. Let's return briefly to complete a full explanation of all the possible parameters that can be specified for each primitive. First, the sphere. What possible values could be changed to affect a sphere? Well, OpenSCAD has only one, the radius. The radius is specified in the parentheses and is the value specified in millimeters. You have to zoom out using the mouse wheel or keyboard, Ctrl- to see the sphere of radius 300 mm, and zoom in to see a sphere of 3 mm. But what's wrong with these spheres? They're not really round. Well, OpenSCAD, like all other programs, has a quick and dirty method of displaying the primitives. It saves time by showing an approximation of the shape we want, but made up of fragments, in this case squares. The smaller the squares, the more refined the sphere can be, but this precision comes at a cost. On the 3 mm sphere, we can insert the line $FN = 30 to calculate an improved sphere. We really make the pie work by specifying 500. Nothing appears to happen immediately in the viewing screen, but check the details in the console, where it's reporting all of the work going on in the background to calculate how a smooth sphere is displayed with so many faces. Finally, this nice round sphere appears, but it will take ages to move around the screen with the current settings on the pie. Resetting the $FN value to say 30, and we can take a look at a cube. Up until now, we've been using the shorthand cube 30, which draws a true cube 30 mm wide by 30 mm high and 30 mm deep. The full command for the cube is cube size equals XYZ, center equals true, where X, Y, and Z are the width, height, and depth in millimeters, and the center, spelt the sensible American way, equals true, is an option that allows you to center the cube at the origin, just like the sphere. Otherwise, the bottom left-hand corner is used. Cylinder is the final primitive. Its full definition is cylinder, H equals 130, R equals 10, R2 equals 40, center equals true. Cylinder, height, radius 1, radius 2, and like the square, center. So in this example, 130 mm high, 10 mm radius at one end, 40 mm at the other. Stop the video now and try to make this shape. In this section, we examined a complete command for each of the primitives, giving us full control over every aspect of each of the dimensions. Now that we have full control of the size of our primitives, we can now transform them. There are a number of transformations. One is colour. Until now, the default colour has been yellow. This can be changed in 2 ways. The first is to simply quote the colour name before the primitive, such as colour again spelt the sensible American way without the U, and then the name of the colour selected from a potential list of over 100 colour names. All of the basic colours can be used, but there are some quite delicate ones such as misty rose, light slate grey and medium spring blue. You can guess the colour names, but some will not work if they're not on the official list. There are some other rules with colour names. All must be selected from the allowable list, are case insensitive, must have spaces removed, and must be contained in double quote marks. A full list of allowable names appears in the OpenSCAD manual, which we'll come back to in a moment. The second method replaces the word with 4 numerical parameters, representing the amount of red, green and blue components, with a 4th value standing for transparency. It's usual to quote colour values in the range of 0 to 255, but in OpenSCAD the values are defined in the range of 0 to 1. Thus we can just specify red, green and blue, or colour mixtures. The 4th parameter is transparency. 1 is full on, and 0.1 is barely visible, and 0 is invisible. Another transformation is position or translation. The translation appears like this, where the primitive is shifted by X, Y and Z along each axis. So here we can shift the cylinder by 10 mm on the X-axis, 15 mm on the Y-axis, and 20 mm on the Z-axis. This formation should now start to become familiar. The style of the translation is the same as the numerical colour formats, both using round and square brackets, and omitting the semicolon at the end of each line. One final transformation is rotate, and here is the familiar format again. Rotate followed by 3 parameters in X, Y and Z, in both round and square brackets with no semicolon at the end. The parameters are given in degrees, so we can rotate by 45 degrees in the X-axis, 45 degrees in the Y-axis, and finally 45 degrees in the Z-axis. Rotate can become quite confusing, and it's here that you might need to consider the small reference axis to work out how your shape's going to rotate. Stop the video now and try to make these shapes with the same transformations. Save each file as an SCAD file and email them to me to be awarded digital badges in OpenSCAD. In this section, we looked at modifying our primitives using transformations. These were colour, translation and rotation. We began this video in 3D as it's a more impressive demonstration of what is possible with OpenSCAD, but 2D is also available and offers some interesting abilities. Here we're going to look at all 3 of the 2D primitives and interesting things that can be achieved with 2D. Dealing with 2D primitives should be easy now that the more complex 3D primitives have already been covered. The 3 2D primitives are circle, square and polygon. A simple circle can be drawn directly into the X-plane by adding circle with the radius in parentheses. Square is the same with the width and height set in the XY planes, even though technically the shape is a rectangle when X does not equal Y. The centre option, again spelt in the American way, allows the square to be centred at the origin of the axes. The final primitive is the polygon, which simply means multi-sided shape. This can be a simple triangle by connecting 3 points, or more complex irregular shapes, just keep on adding coordinates. There would be little in using 2 dimensions if it was not for OpenSCAD's ability to extrude, an extrusion. Extrusion forces out the shape into a 3rd dimension, just like toothpaste. We can work through an example given in the documentation to demonstrate what can be done with the extrusion. First, take a plain circle that looks like a hexagon, as this is OpenSCAD's quick and dirty drawing style we demonstrated earlier. Circle r equals 1. Now translate it slightly off centre. Translate 2, 0, 0. Now we can extrude this shape up the screen and centre it to make it easier to track. And twist the extrusion. Or twist it more back the other way. Or smooth it out. Or really make the pie work by adding more fragments to make the shape very smooth. Linear extrusion extrudes the shape up the Z-axis. Replace linear with rotate to make the extrude around the Z-axis. This completes all of the methods of creating 2 and 3D dimensional objects. Stop the video now and play with linear and rotational extrusions. In this section, two-dimensional primitives of circle, square and polygon were introduced. These were then extruded into 3D, easily producing shapes that would be difficult, if not impossible, with 3D primitives. So let's review what we've seen in OpenSCAD to date. We've seen that it allows us to generate 2- and 3-dimensional shapes. The 2D shapes are circle, square and polygon, and the 3D shapes are sphere, cube and cylinder. We are free to change the colour, size or position of any shape and can distort them by extruding 2D shapes or intersecting, combining or subtracting 3D shapes. It's a little like being shown all of the options available in Lego bricks. Like Lego, it may at first seem simple, but really complex pieces can be constructed from a very simple set of commands. There is no easy route to learning SCAD. Experimentation is vital. In this next section, we look at some of the techniques that can be used to simplify the design process. We have covered a good deal of the basic functions available in OpenSCAD, and if you have paused the video as requested, you should by now have gained a good deal of confidence and experience in the application. With these new skills, we can now move to the next stage, which are the techniques used to generate more complex objects more efficiently. So let's begin with the small plate, 6x6x1, into which we want to centrally place a hole which is a cylinder radius 2, the same thickness of the plate, which is also 1. This cylinder needs to be placed at the centre of the plate, so we need to translate it halfway on the width on the x-axis and halfway on the height on the y-axis, and the thickness z is the same as the thickness of the plate. It's a hole, so it needs to be subtracted using difference, F5 to re-render it. Now, you may have come across this flashing grainy surface. This is OpenSCAD's method of reporting the problem. The plate and the hole are exactly the same thickness, so these ends are impossibly thin. Press the F6 key to produce a better render. Now what I want to do is make a bigger plate, say 8x8x1. Well, simply change the 6x6 to 8x8 like this, and the hole now is not in the centre. We need to change these values of 3 to 4 and re-render with F5. Now this is a fairly long and error-prone process, just to change a simple dimension. There must be a better way. Well, there is. The solution is to create what is known as a module. Enter the word module here and name it plate up here, and surround everything that means plate in curly brackets. If this is run, nothing happens, but now, if I type plate in here, it will run plate and display. But this will not solve the size problem. We'd like to specify any size plate and let the module plate do the work. To produce a module that can draw a plate of any size, start by taking a working module. Next, make a list of the items that may be changed. These are called variables. The variables we'd like to change on the plate are the length of the plate, as seen on the x-axis, the width of the plate, seen on the y-axis, and the thickness, given on the z-axis. It would also be useful to specify the radius of the hole. Now we can choose names for these variables. Any name can be used, but it would be useful if they were descriptive. So let's use length, width, thickness, and hole. Insert these names in between the parentheses here, following the module plate. Now these variable names replace the numbers in the body of the module. So, length, width and thickness drop directly into the cube parameters, and thickness and hole drop directly into the cylinder parameter. But remember the problem of the position of the hole. In translate, the two values have 4 to be replaced by half the length, length divided by 2, and half the width, width divided by 2. Now this translation will also change with the length and width of the plate. Finally, we need to insert a few values here to test the module is working. Yeah, seems that's it. Flush with success, let's see whether we can expand the plate to produce a bracket. Module bracket is a plate combined with the same rotated by 90 degrees. This produces a bracket, but there's a slight problem due to the thickness of the plate. To make sure each side of the bracket is the same and the corner is square, we could add, or union, a thin cuboid, shown here in blue, to fill the corner space. We can test a few values to show the bracket calls plate twice and works correctly. We could continue to build more and more complex shapes, testing and building with a greater confidence, providing that everything works at each stage. This is not just how OpenSCAD works, but how computer programming in general grows. One final point before we move on. Our single plate and bracket model allows us to design our own more complex primitives. We do not need to have hundreds of models of plate and bracket for every possible size, as just one of each suffices, so long as we feed the variables we want. The name for this type of model is parametric, and again is found in conventional computer programming. It has the advantage of allowing us to build libraries of known good working shapes to be reused and even shared with other designers. Parametric modules were introduced in this section. Modules could be considered to be customized primitives, groups of primitives combined for repeated reuse. Modules that included variables are known as parametric models and are even more powerful and flexible. These characteristics means that they can be stored in libraries for future reuse and sharing. Why reinvent the wheel? In this section, we will follow a design process as an introduction as to how programmable OpenSCAD is, and how functions normally seen in software come alive as they're demonstrated in this 3D environment. We will try to build a column as a working example. We can start with a cylinder. Choose any size, say height 600, radius 10. That's fine, but we can do better as columns have flutes, which can be generated by removing smaller cylinders from the first column's edges. Let's turn the column transparent to see the effect of the second cylinder at the edge. We can delete the smaller cylinder from the larger one to produce the flute using difference, and then use rotate to remove the next flute like this, and the next, and the next. But if you've ever seen something constantly repeating like this, you know there must be a better way, and of course there is. Here we can use what is called a for loop. Combining all of these lines, we say that for n equals 0, 1, 2, 3, 4, 5, all the way up to 24, we can carry out whatever is in the curly braces. Note, the very much more compact way, the same effect can be gained due to the for loop. We can move the flutes up from the base by translating the whole lot up 200 to provide a plinth. This is fine, but exposes a nasty square at the end of each flute. So let's try to round these off. To help with this, we can modularize flute, like this, and place flute as a module. Now let's focus on the flute by placing an exclamation mark in front of it and rounding its end by adding a union with a sphere. Now, a nice rounded edge. Let's see the effect on the whole column. Well, that's an improvement. Now that it's working, we could now turn the whole thing into a module called, say, column, and call a module like this to display it. We met parametric models in the previous section. We have a working column, so let's make it parametric. The next step is to select the key parameters. Let's start with diameter. We can change these radius values to be the diameter d, and can add another column of a different diameter. That all seems to be working. This example is based upon an excellent video that can be followed here. In this section, we saw how to simplify a design by compressing repeated instructions using a for loop. This completes our introduction to OpenSCAD on the Raspberry Pi. If you have stopped the video and followed the examples, then you will have gained a good deal of experience in using OpenSCAD. You will certainly have made your Pi work. We began by looking at the 3D primitives, sphere, cube and cylinder, and how these can be combined in union, or reduced by difference and intersection. We then learned about transformations that change size, shape and colour. 2D primitives of circle, square and polygon could be extruded into some wonderful shapes. Modules allow us to design our own primitives, and parametric models further enhance the power of the system by adding variables, making designs far more flexible, reusable and even shareable. Finally, we reduce repeated designs by using for loops. Most of our focus has been on the text editor in the viewing area, but those who have looked at the console window would have seen how hard the Pi was working. This is only an introduction, and should you wish to go further into animation and 3D printing, then you'll probably be better off downloading OpenSCAD onto a more powerful machine. Downloads for OpenSCAD are available for other versions of Linux, Apple and Microsoft machines. There's a wealth of help and support available online. Here are a few, some of which are the source examples for the material in this video.